So, welcome back to another episode for our first part of Module 4, the Differential Amplifier. So, last episode, ang pinag-usapan natin is the differential pair. So, yun yung pinakapuso ng isang differential amplifier. An amplifier cannot be a differential amplifier kapag wala tayong differential pair. Ngayon, alam na natin yung purpose sa differential pair, siya yung kumokontrol kung sino yung merong mas mataas na kuryente. So, pupunta na tayo sa differential amplifier itself. Previously, in the last episode, meron tayo dong differential pair, di ba? Tapos merong nakalagay sa tuktok no na box. Tapos may pangalan nyo na load. So, lalagyan na natin ngayon ng laman yung box na yun. Okay? So, for this episode, pag-aaralan natin yung differential amplifier with resistive load. So, ito pong itsura ng circuit ng isang differential amplifier with resistive load. So, kung mapapansin nyo, similar siya dun sa experiment number 3 nyo. I think experiment number 3 yon sa LX Lab, di ba? Ito po yung differential amplifier. So, meron pa rin po tayong differential pair, which is a pair of identical transistor. So, in this case, NPN. Tapos, meron tayong current source connected dun sa emitters nila. And yung load kanina, pinalitan natin ng dalawang resistor na pangalan IRL. Okay, sir, nung sa experiment namin, wala naman ako natatanda ang gumamit kami ng current source. So, pwede rin po kasing resistor lang yung nandyan. So, ganun po yung mga dating topologies for differential amplifier. Resistor lang yan. Pero yung mga bago pong circuits, wala po kayong makikitang resistor lang dito. Laging current source yan. So, again, the definition po ng differential amplifier, it amplifies the difference in voltage ng node 1 and node 2. So, kukunin yung difference ng VI1 and VI2, which is VI1 minus VI2. Then, i-amplify niya po yun. So, yung output ng ating differential amplifier can be single-ended or with respect to ground or differential. In this case, we have a differential output po. So, our output voltage is measured between node VO1 and node VO2. Or simply, it's VO1 minus VO2 po. Okay, so ang focus natin dito is to do DC analysis ng differential amplifier with resistive load. So, if our differential amplifier is operating in the quiescent condition, so pag quiescent po, ibig sabihin quiet ang ating amplifier. Or ibig sabihin nun, wala po tayong AC input voltage. Wala tayong ina-amplify. So, for quiescent operation, ang currents IC1 and IC2 should be exactly the same po. So, to make this the same, dapat IC1 is equal to IC2, tapos dapat siya ay kalahati ng ating ITAIL. Dahil kapag nag-KCL tayo dito sa node na yan, ang sum dapat ng IC1 and IC2 should be equal to ITAIL. So, meron silang tig-kalahati ng ITAIL. So, para magawa yon, kailangan meron tayong biasing voltage sa VI1 sa VI2. So, dapat may DC voltage tayo dyan. Okay, so gagawin natin is meron dapat tayong VBB1 from here to ground. Okay? And we also have VBB2 in this node to the ground. Okay. So, ano kaya ang value ng VBB1 and VBB2? Magkaiba ba ang values ng VBB1 and VBB2? So, ang hint dyan is titignan natin yung current sa IC1 and IC2. Sabi natin kanina, at quiescent operation, dapat IC1 is equal to IC2. So, ibig sabihin, dapat yung VBE1 is equal to VBE2. If VBE1 is equal to VBE2, ibig sabihin nun, the biasing voltages VBB1 and VBB2 are equal po. So, kikita natin dyan, kapag equal si VBB1 and VBB2, pag bineasure natin yung differential voltage between I1 and I2, makikita natin siya ay 0. So, hindi natin nakikita tong voltages na to kapag nagme-measure tayo ng differential signal. So, ano ibig sabihin nun? So, ibig sabihin nun, it is a common mode voltage. Okay? Dahil parehas yung amount ng voltage at this node or sa input 1 and sa input 2. So, effectively, siya ay common. So, this biasing voltage will be called as the input common mode voltage or VICM po. So, what should be the value of VICM then? So, we need to set the VICM para mag-operate yung ating differential pair in the active region. Dahil this is an amplifier po, di ba? Ang amplifier, it operates in the active region. So, ang ating conditions, dapat VBE1 is equal to VBE2, which is around 0.7. And VCE1 or VCE2 should be greater than the saturation voltage ng ating transistor. So para ma-analyze natin na mabuti yan, kailangan natin mag-KVL. Diba? So since itong part na circuit na yan, and this part of the circuit ay identical, pwedeng mag-KVL lang tayo sa isang part. Parehas lang po lalabas, diba? Okay, so mag-KVL lang tayo dun sa left na part ng circuit. So by using output KVL, makita natin that VCC is equal to ICRL plus VCE1 plus VE or the voltage at this node. And for KVL naman sa input, we have Vicm, which is the biasing voltage na connected sa input 1, is equal to VBE1, base emitter voltage, which is around 0.7, plus VE. So actually sa ating input loop equation, since VBE is almost constant, makikita natin that the voltage VE is actually dependent to our Vicm, or the input common mode voltage, or the DC biasing voltage. So, makukuha natin dito yung equation of VE, which is VE is equal to Vicm minus VBE. Then, gawin natin is, we will plug in this VE dito sa ating output loop equation. So, therefore, VCC is equal to IC times RL plus VCE plus Vicm minus VBE. So, ang ating concern pagdating sa output loop equation is we need to check that VCE is greater than the saturation voltage VCE sat. Diba? So, kailangan natin i-transpose to mga to sa kabila. So, the worst case in our output loop equation is kapag maximum po si input common mode voltage. Dahil kapag maximum si Vicm, actually VE is mataas. If VE is mataas, and we have a constant current dito na I tail over 2, ibig sabihin yung VCE1 natin needs to decrease. Okay? So, VCE1 will decrease. So, hanggang saan ba pwedeng mag-increase ang ating VCE? So, ayun nga, sabi kanina, the minimum voltage for VCE para mag-operate ang ating transistor in the active region is the VCE sat. Kaya nagkaroon tayo ng VCE sat dito. Hello, Sir G from the future. So, kaklarify ko lang po itong area na to. So, si VCE kapag equal siya sa VCE sat, our VE should be at its maximum, di ba? And kapag maximum po si VE from the input loop equation, maximum din po ang ating input common mode voltage. Kaya biglang nagkaroon ng Vicm max po dito. Yun lang. Bye-bye! Di ba? So, therefore, the maximum input common mode voltage is VCC minus ICRL minus VCE sat plus VBE. And if we want to represent this in terms of I tail, not IC, gagawin lang natin, IC will be I tail over 2. So, magiging Vicm max is equal to VCC minus I tail times RL all over 2 minus VCE sat plus VBE. So, ito po ang ating maximum input common mode voltage. Okay? As long as the DC biasing voltage na nakakonect sa ating inputs is less than Vicm, ang magiging current natin dito will be I tail over 2. Okay. Next naman. So, kung meron tayong maximum value of the input common mode voltage, meron din dapat tayong minimum. So, sa minimum, it is dependent ngayon sa input loop equation natin. So, what is the minimum voltage of our biasing voltage Vicm? So, recalling kanina that Vicm is actually equal to VBE1 plus VE. So, si VE meron niyang minimum voltage para mag-operate. Because this is a current source. Kasi ang current source, pwede natin palitan yan ng transistor in active region. So, may minimum voltage po si VE. So, therefore, the minimum input common mode voltage or the DC biasing voltage will be VBE plus the minimum voltage for the current source to operate po. So, therefore, meron lang tayong range ng input common mode voltage or range ng VBB. This is the biasing voltage. So, it is from minimum to the maximum. Okay? From VBE plus VE min to this expression. So, that's it muna for this episode. Diniscuss lang po natin ano yung range ng ating biasing voltages para mag-operate ng tama ang ating differential amplifier with resistive load. So, for the next episode, magsasolve lang tayo ng sample problem. So, I will see you in the next one. Bye!